What will Vera Rubin find? Can life on Tau Ceti be found? Why do we find galaxies at different ages at the same angular size? And in Q&A Plus, which is the closest planet we could find life at? All this and more in this question show. It's time for the question show. Your questions, my answers, as always, wherever you are, across my channel. If a question pops in your brain, just write it down. I'll gather them up and I will answer them here. All right, let's get into the questions. Pete Rund. Will Vera Rubin vitalize the possibility of Planet 9? Vera Rubin is the best tool to find Planet 9, if it exists. And in fact, at the time that we're recording this now, we are almost a week of Vera Rubin operations, with it finding about 800,000 objects a night. Interesting alerts, supernovae, transients, active galactic nuclei, asteroids, comets, and eventually, if it's out there, one of those things will be Planet 9, or, Planet 10 if you think Pluto's Planet 9. I don't take a position in this fight. The next planet, because the current crop of telescopes have, and the kinds of all sky scanning that has been done so far has failed to pick it up, which means that it is fainter, smaller, farther than what the current survey telescopes are able to find. But Vera Rubin is just next level. Vera Rubin is an entirely different creature, able to see objects that are much fainter and to track any kind of movement that's going on in the sky. So when will we see it? I should actually talk to somebody about that. I've got an interview coming up with someone from Vera Rubin. We're going to be talking about the data pipeline side of things. And so maybe he'll know about Planet 9. But maybe I'll just talk to Mike Brown and sort of find out what their plans are to search for Planet 9. But if it's out there and it's possible to find it, Vera Rubin will find it, as well as, 800,000 other things every single night. But one of those could be Planet 9. Josh Miller, is Vera Rubin currently scanning in the direction that we suspect Planet 9 might be? Well, Vera Rubin is scanning in all the directions. Vera Rubin is taking a full image of the entire southern sky every 3 days. Just relentlessly, night after night after night. Take a picture, 15 seconds, take a picture, 15 seconds, take a picture. It does the whole sky. So is it scanning the direction that we suspect Planet 9 might be? Yes, because Planet 9 could be anywhere in the sky and Vera Rubin is going to catch it. Now, that's not entirely accurate because Vera Rubin is positioned in the southern sky. It's down in Chile. And so it can only see the sky that is visible from its perspective. But it has a really good view of the plane of the ecliptic. That is sort of where in the sky all of the planets are bunched up. And so it's expected that, if all of the planets have been found in this very thin band in the sky, that Planet 9 will be there too. Now, other objects have been found on extremely highly inclined orbits like Eris. Eris is at like a 44-degree tilt from the rest of the solar system. Even Pluto is like 17%, so it's pretty highly tilted. But the safe bet is that Planet 9 will be in the plane of the ecliptic, especially if it's big. Because it would have formed out of the protoplanetary disk with all the rest of the planets. And so it would be orbiting like the rest of the planets are. And so that's where you start. And the ecliptic is well positioned in the sky for Vera Rubin. And so it will be scanning that and even putting a little extra emphasis on that region because there's most of the asteroids, most of the comets, dwarf planets, they're all going to be in this thin band in the sky. And when new telescopes are developed, the sort of power move that astronomers make is they scan the ecliptic because that's where you're likely going to find things. So when the Very Large Telescope was built, astronomers used it very quickly to find Eris, Haumea, Makemake, Sedna, all of these various large Kuiper-belt objects, all these dwarf planets were all found because you had a more powerful telescope, you scan the area where the planets are, or where all the things are likely to be, and you'll find stuff. And so that is the region of the sky that Vera Rubin is probably going to find things. And it is, it's very well positioned to be able to find that. Perry M. The closest G-star to us is Tau Ceti at 11.9 years. Is that a good candidate for Vera Rubin to find terrestrial world close to us in a stable star system? Unfortunately, Vera Rubin is not good for that kind of thing. Theoretically, Vera Rubin can help find exoplanets because it's looking for changes. And so it's going to see dimming of stars and then brightening of stars, and that you could then correlate that to planets passing in front of stars, but it's going to take more detective work to be able to figure that out. But it is just not the best machine to be able to find that. The one you probably want is the Plato telescope, which is going to be a mission launched by the European Space Agency in about 3 years from now, 2 years, 2028. Yeah. And so if there is a planet that is aligned in front of the star from our perspective, is passing in front of the star, right? Then, and blocking the light of the star, then, and only 11.9 light years away, that's very close, then Plato probably would be able to spot it. But if that was already there, I mean, people have done surveys for planets around the closest stars. TESS is doing it right now. And if there was one there, we probably would have noticed. Like, we found a planet at Proxima Centauri, multiple planets at Proxima Centauri, and it's a red dwarf. But it would be amazing, right? The closer the planet, the better, because then our biggest telescopes can try to examine them. FL photocatcher. Why does telescope interferometry need to combine the light from telescopes that arrived at the same instant to work? If the object image wasn't changing so much, I don't see why it wouldn't work. So the trick with an interferometer is that it allows telescopes that are separated with nothing in between them to act as if they are a telescope the size of their separation. So in other words, you have two telescopes, they are a kilometer apart, and they are looking at the same target. Then it is if you had a telescope that was 1 kilometer across. Imagine you have a telescope that is 1 kilometer across. That's a very big telescope. And that allows you to have resolution. So you can pick out features that are very small. The resolution that you have is of a telescope that is as big as 1 kilometer across. What you don't get is the sensitivity. So you don't get to see faint things. You have to see bright things. But if you have, say, two stars that are orbiting around each other and the stars are very bright, you take your telescope and you look at the stars and you can't tell that the stars are separate. And then you take two telescopes and you put them side by side and you move them apart. Eventually, you'll get to a point where you can actually tell that it's two separate stars that are orbiting around each other. And that is interferometry. And so people always ask, like, could we just take the world's telescopes and add them together and to make one big telescope? And the problem is that it doesn't work. They need to be on the exact same wavelength. And that's the thing that you were mentioning in your question. And so, a way to sort of think about this is that this is how a regular telescope works. Like, a regular telescope lens is an interferometer, in that you have wavelengths of light that are coming from distant objects. Photons are coming from distant objects. And then they are hitting the lens of the telescope at the exact same time, or within the nanometer give that they require. And then they are bouncing off of the mirror, and then they're being focused into whatever instrument you're using, or your eye. And so if you want the baseline, if you want the resolution, then it has to be the same wavelength, it has to be essentially the same photon. This is why for the Event Horizon Telescope, which is this network of telescopes around the world, they were using radio waves, because radio waves are giant, right? Radio waves can be tens of centimeters, a meter across. And with that, you can use atomic clocks. You know exactly when the radio waves were collected with your atomic clocks. And then on computer, you can then do the interferometry. You can mash them together after the fact. But if you're using very narrow wavelengths like visible light, like ultraviolet, like infrared, you have to do this in real time. And so you actually have to have some mechanism that makes sure that you're getting exactly the same photons. Now, you can combine the light from several telescopes. That will give you more sensitivity. So in other words, if you had two identical telescopes side by side, and you were okay with them not receiving their photons at exactly the same time, then you would just have the equivalent of the two telescopes. You had 1,000 telescopes, you have the equivalent of 1,000 telescopes, but you don't get that resolution, that baseline, that ability to pick out features on the surface of stars really far away until you build the interferometer. And that's why the Chara array, I've done an interview on the Chara array, the telescopes themselves are fairly modest. They are a couple of meter telescopes, but they're separated by hundreds of meters. and they are aligned in this really complicated way so that they have carts that move back and forth. As the object that they're tracking is moving through the sky, the distance that the light goes to get to the different telescopes changes. And so they have to have these carts that move back and forth to make sure that the telescopes are still aligned again. And they can see features on the surfaces of stars. They can pick out stars that are orbiting around each other. It's an incredible technology, but you've got to get down to that level of precision. And when you think about the wavelengths, right, of visible light, they are in the hundreds of nanometers. Like, that is a tricky measurement to be able to make. It's time to shout out our new patrons at the $5 level and above. Funky Loiso, Janice Smith, E.T., Call Me Mose, Kevin Danielson, Lucas Cooper Bay, Satyricon, Judy Sutherland, Carl Perone, and Kevin Byram. Join our community at patreon.com/universe today. And Skeptic Y2, why do galaxies a billion light years away look the same size as a galaxy 50 million light years away when a big telescope takes a picture with them in the same field of view? When you see a picture of a galaxy, you don't know how much of the field of view of the telescope you are actually seeing. So the biggest telescopes have really huge CMOS sensors, like the camera that is capturing the image is enormous. The one in the telescope behind me is a 3000 by 3000 pixel CMOS, and Vera Rubin is tens of thousands pixels across. And it has this really wide field of view. And then it will take an image, and some number of the pixels on that telescope will have the image of the galaxy on it. And then the astronomers will crop into that part of the image to be able to display it on news releases, but also to study it for the science. And so you have no idea what was the field of view of the telescope. This telescope has about a half degree field of view, so it's like a little bit bigger than the moon, like maybe twice as big as the moon, actually. 0.56. Anyway, it's bigger than the moon. But others, for example, say James Webb or even the Hubble Space Telescope, are a fraction of the moon. They can only see this tiny little postage stamp version of the sky, while Vera Rubin has this gigantic wide field of view, many moons across. And so all of the factors are the size of the aperture, the field of view of the telescope, the speed of the telescope, the size of the sensor that the images are being captured onto, and then the final crop that the people do. Like, they literally take the image and they crop into the part that they want, and they copy paste it and they put it into whatever they need. And it's funny to me, when you see the astronauts on the moon and you see pictures of the Earth, people make some kind of judgment about how big the Earth is from the picture, but you can't make any judgment about the size of things taken by a picture, because it all depends on the lens. If you have a wide angle lens, then things look small. If you have a telephoto lens, then things look big. If you crop in, if you have a big sensor on your telescope or on your camera, then you can zoom in on that little part and reveal that. So it's sort of like not a reasonable thing to argue about. But in your case, yeah, the size of the objects have many different factors. You know, you can see that they start to look bad, right, when they're really far away and you're not able to make out really nice spiral arms. But generally, when you look at a picture of a galaxy taken by Hubble or James Webb or whatever, if you can see the spiral arms and there's like a lot of structure and you can see little knots of star formation and the galaxy looks really cool, then it's in the tens of millions of light years range, right? Out to 200 million, 300 million light years away. If the galaxy like clearly has a spiral shape, but all you can really see are sort of large scale features of it, then you're in the hundreds of millions to a couple of billion light years away range. And if you can sort of have a hard time telling whether it's a spiral galaxy or not, then you're out to 5 billion, 8 billion, 10 billion light years away. It's the quality of the resolution of the image that will be your sign for how far away that galaxy is. Did you know that you can watch the same video with no ads and get a bonus question over on Patreon completely for free? We call it Q&A Plus. This week's bonus question: which is the closest planet that we could find life at? And I'll put a link in the show notes. All right, those are all the questions that we had this episode. Thank you, everyone who asked your questions into the YouTube comments, everybody who joined me for the live show. The time for the live show has kind of been moving around at different times because I've been having to cancel it so that I can do work on my telescope when there's dark skies. Anyway, things should settle down at some point. I'm going to talk about a movie that I never watched that I should have. But first, I'd like to thank our patrons. Thanks to Abe Kingston, Andrea Pedretti, Barely Griffin, Brian Bodie, Caradwin, Chuck Hawkins, Commander Baylock, Cooper Nelly, Dark Finger, David Gilton, David Matz, Evan.pro, Greg Feely, James Clark, Jeremy Madden, Jim Burke, Jordan Young, Josh Schultz, Marcel Switz, Micah Purcell, Nordspace, OneStepForAnimals.org, Powerbuck, Rankaidu, Richard Williams, Sean Sargent, Stephen Feathermunley, Team 49, Telescopes Canada, Wolfgang Klotz, and Zeldaborg Galactic Defender, who support us at the Master of the Universe level. And all our patrons, all your support means universe to us. So now that I'm on my physical media buying kick, here's my collection over there. I've been buying DVDs. There was a movie that was at the thrift store, and I was like, oh, I should grab that. That should be part of my collection. And that is The Right Stuff, which tells the story of the Mercury astronauts. And it's funny because I had these sort of really vague memories about the movie. I didn't really remember any part about the movie, only sort of like the last scene. And I was sort of like talking to my wife about this as we were watching. And then I realized that I had never seen the movie. I've never seen The Right Stuff, which is crazy because it is sort of one of the core fundamental space exploration movies. So it's just got me like, okay, now I need to go and rewatch all of them. So you've got The Right Stuff. Obviously, you got Apollo 13. There's The Dish, which is a movie about attempting to communicate with the moon landing. There's Hidden Figures, about the mathematics that went into the moon landings. And then, of course, there's From the Earth to the Moon, which is a TV series about the moon landings. And I'm sure there's a bunch of more stuff that I've forgotten. Oh, October Sky. So yeah, if you haven't watched all those and you want sort of like a great historical retelling of what happened to have humans first land on the moon, those are a bunch of great movies. And I'm glad that I finally watched The Right Stuff. It was great. I really enjoyed it. All right, we'll see you next time.